Exciting developments in Oxide TFT technology. What does this mean? Well, Oxide TFTs are getting a lot of publicity the last couple of years. Active matrix liquid crystal displays are the main flat panel display technology. This is one of the things that really got people excited. A couple of years ago, and just about 2 years ago, Sharp announced they were going to commercialize Oxide semiconductors. And so this created really a very, very big stir in the industry. Another thing that happened, active matrix organic light emitting devices are an emerging technology that a lot of people have been very, very interested in. It turns out at the SID Display Week last year in Boston, LG showed a 55-inch television that was just about that thick. It was a beautiful, beautiful television. And so again, a key aspect of that is they were using these Oxide TFTs, oxide thin film transistors in that. Again, look at some of the other hype. E-paper, a lot of electronic paper applications emerging. Here's just an announcement of AUO. They're one of the leaders in Taiwan. They made an announcement a couple of years ago. They're moving to oxides for flexible oxide TFT electronic paper or e-paper. Tablets. Looks like we're going to see a lot of this technology in tablets. Here's an announcement from Samsung just showing, again, a couple of years old now, but showing that they're moving with this Oxide TFT technology to tablets. Transparent displays. They're very much an emerging technology. It's not here yet, but it's a very exciting technology. Display Bank is predicting very big things. It's always easy to predict high growth when you're far enough into the future, so whether you believe it or not is something. But they've got a lot of people excited by these projections. A lot of the industrial guys are saying transparent displays are going to be one of the next big things. If you want some of the hype on the internet, go to A Day Made of Glass by Corning. It will really capture attention in terms of what transparent electronics can do in terms of revolutionizing all kinds of things. There's two A Day Made of Glass. Another one that's very good is this a Samsung Smart Window. A Day Made of Glass is mainly looking into the future and saying, well, here's maybe where things can go. This is actually a prototype. It's about a year or two, it's about a year old now, but a very, very impressive prototype that shows that some of this technology is not very far away. Sharp is advocating Oxide TFTs as creating a full display platform where they're looking at LCD monitors, tablets, high-definition notebooks, and actually more than what they list here. This was just from last year. They've revised this upward. So what's going on here? This is pretty exciting, especially for those of us who have been working in this area for a while. So where did all this come from? Well, I would argue a lot of it began with transparent electronics. And so you say, well, what the heck's transparent electronics? Maybe you haven't heard of that. It's electronic devices which are optically transparent. Might look something like that. That's a demo that's come out just very recently. They're see-through. There's another one. They're invisible or almost invisible. Again, another prototypes of things that are emerging or people's ideas of what will emerge. More precisely, they're transparent in the visible portion of the electromagnetic spectrum. Now, we like that idea so much that in about 5 years ago, 2008, we wrote the first book on transparent electronics. Since then, there's been 2 other books on transparent electronics that have emerged in the last couple of years. There's the covers of those 2. And then there's another one that's come out where there's quite a bit on transparent electronics. The title is not transparent electronics, but it does deal with some of the transparent electronic things that are going on here. So really the heart of transparent electronics is what we call the transparent thin film transistor. So let's look at that. It comes in a couple flavors. This is the most common flavor. This is a bottom gate staggered thin film transistors, if you care. You don't care, it's just a transistor. And the gate part of that, the part that controls the electronics, is made of a TCO or a transparent conductive oxide. This is often indium tin oxide. You can think of it as a metal, except it's a see-through metal. So everywhere I put a TCO, it's like I'm looking at it as a metal, but it's transparent. So that's the gate. Let's say that's the source, and let's say that's the drain. Right away, we see something very, very, very interesting from the point of view of the importance of this technology. And that is that I can put the TCO right on the channel, and I don't have to do anything to make contact. That turns out that's huge. No channel doping is required for source-drain contacts. You'll see in terms of LTPS, low temperature polysilicon, that's our main competitor. This is huge. Can't overemphasize that, okay? So continuing the saga, what we've got is this is a metal insulator metal kind of structure in terms of the gate control. And I say metal in quotation marks because TCO is really not a metal, and the semiconductor, the channel layer is, well, it's kind of a semiconductor, but kind of something else. Anyway, that's the basic control structure that we're using in this TFT, thin film transistor. Let's see how that works. So let's ground the source and ground the drain. Let's apply a positive voltage to the gate. What happens is we induce electrons towards the channel. And so it turns out these channel layers are N-type materials. That means they have some electrons, but very, very low concentrations of electrons. So when we apply that positive voltage, what we do is we accumulate electrons in an accumulation channel. That's different than a MOSFET. Silicon MOSFET is an inversion channel. This is an accumulation channel. And then to see how it works a little bit more, let's put a positive voltage on the drain. What happens is we get injection of electrons from the source, transport of electrons through the channel, and extraction of electrons out the channel. That's the basic operation. Something else that's different about silicon MOS technology, what happens is the first electrons we put into the channel get trapped. That's different than silicon. Silicon doesn't behave that way. So again, it's similar in some ways to a silicon MOSFET, but it's different in other ways. Obviously, since it's transparent, it's really different in that sense, but the electrical operation is somewhat similar. So the very first one of these that we did way back in the Stone Age in 2001 was zinc oxide. And we got a lot of media attention when in 2003 we published our first paper. Got picked up on all kinds of media all over the place. We got a lot of hype on this. And the reason is, one of the reasons is it's transparent, but the other reason is we were using zinc oxide. That's the stuff you put on your nose when you go to the beach. And so people thought, well, this is really bizarre and weird. How can you see through electronics? And what the heck, you know, it's the same stuff you put in the beach. So people like that. In fact, everybody was putting it on their nose at that time. I'll come back to him in a little bit. But zinc oxide was one of the materials. We looked at tin oxide, so you can think that rust on a tin can we were using. Indium oxide is another material that we used. And really, when we would go to transparent conductive oxide conferences and talk to them about it, they thought we were nuts because we wanted to do transparent non-conductive oxides. Most of the guys in transparent conductive oxides have spent their entire career trying to make their materials more and more conductive. If our materials were conductive, they wouldn't work. So we tried to make them as unconductive as possible. And so they couldn't figure us out either. We were confusing a lot of people back then. Here's one of the early papers we did back in 2004. This is just showing the level of transparency, both the raw data and then corrected after reflection. And this is a tin oxide device. It was a difficult device to make, it turns out. But there's a problem with it. It's polycrystalline. Polycrystalline, I'm going to argue, this is not a good thing. So why? Here's my contention. I contend that from a manufacturing point of view, amorphous materials are more attractive than polycrystalline materials for large area electronics applications, such as display applications. So why? Why is that? Well, there are no grain boundaries. That's the essence of most of it. And if you have no grain boundaries, you have better uniformity, controlling the uniformity across very large glasses. Gen 10 glass is 3 meters. It's from here to that door. It's that big. So you gotta uniformly coat that huge piece of glass. That's very difficult to do with a polycrystalline material. Also, grain boundaries are the sinks and source of garbage. A lot of the stuff that you don't want goes into the grain boundary, comes out of the grain boundary. Controlling the electrical, optical properties with grain boundaries is a difficult challenge. It turns out amorphous materials have ultra-smooth surfaces, approaching atomic smoothness. This is very nice when you're integrating, especially over meter dimensions. Usually, amorphous materials require lower temperature, which is always a good thing from a manufacturing point of view. So I tell my students, grain boundaries are the enemies, and so we just say no to polycrystalline. That's one of the main messages, kind of loud and obnoxious, but that's one of the main messages of the talk. You say, how do you do that? Well, here's the sweet spot of the periodic table as identified by Professor Hosono at the Tokyo Institute of Technology. That's the guy who was wearing the zinc oxide before, who I'm going to terrorize in this talk. And he pointed out before transparent transistors existed, this was when they were trying to make amorphous transparent conductive oxide, he pointed out that this is the sweet spot of this periodic table. And here's how it goes. If you tried to make zinc oxide, no matter what you did, it's always polycrystalline. If you tried to make tin oxide, like we did, and I showed an example, it's always polycrystalline. You can't make it amorphous. With indium oxide, I went by that quickly, it turns out you can make it amorphous, but you really have to struggle. It's a very difficult thing to do. So his solution was, let's use multi-component combinations. Let's use, let's say, 50% indium, 50% tin. And what happens then is you can form an amorphous material, and it stays amorphous usually until about 450, 550 degrees, somewhere in there. Okay? So that's one combination. Another combination is zinc and indium oxide, ZIO. That also you can make an amorphous material. One that we've worked with quite a bit is IGO, indium gallium oxide, and the current world favorite, the one that's going into production, we call it IGZO, indium gallium zinc oxide. And part of what's going on is if you look at the three main combinations, indium oxide, tin oxide, and zinc oxide, they have different crystal structures, radically different crystal structures. So when you combine them in 50-50 combinations or things like that, the lattice doesn't know which way to crystallize. There's a kind of a crystal frustration there. And because of that, the morphology remains amorphous. That's really one of the main secrets about this. And this is good for the amorphous oxide semiconductors because if we have a crystalline material or if we have an amorphous material, it turns out that the conduction band is made of 4s, 5s, or 6s spherically symmetrical atomic orbitals. And so the electrons can essentially propagate from one orbital to the other, and the electrons don't care if you have an amorphous microstructure or if you have a very periodic crystalline microstructure. You can propagate the electrons very readily through that. That's in contrast to silicon. Crystalline silicon is 1,000 times higher mobility than amorphous silicon, and that's because crystalline silicon is a covalent material. You have to get the bonds just right, matched perfectly in order to get good mobility. Here, because of the nature of the bands, it doesn't matter. It's much, much more forgiving. So when I look at this, one of the things I see is I see a new class of electronic materials, and I always like to think about the students in the class. Some of them are kind of toxic, and I don't really like dealing with them. Some of them have an attitude, and these guys are kind of expensive, but I'm looking for the A and B students, the remaining A and B students here, and we have really all kinds of, a whole cluster of new materials possibilities. I'll focus mainly on IGZO. Now, if we look back to the 2003, 2007 sort of time frame, we did a lot of work on transparent thin film transistors, and really we were the freak show. We get invited to places because this is so weird. I mean, you put zinc oxide on your nose and you see through. It's like, people would ask you, well, okay, but what are you going to do with it, and what's it good for? In fact, a lot of the industrial guys said, well, call me when you grow up, We did not get a whole lot of respect back there in that time. But things abruptly changed at a meeting in Long Beach in 2007. I was invited to give an invited talk. I was very excited about it because I thought, well, maybe they're taking us seriously. And then I looked at the program, Professor Hosano and I, in a very nice paper from LG Group. But they scheduled us for 4 o'clock in the afternoon on a Friday. And I don't know how your conferences go, but usually it looks like this at 4 o'clock on Friday. It's you and the session organizer and the janitor waiting to clean up. And, you know, it's pretty bad. I was just shocked. So I had a bad attitude going in. I was shocked. It was not quite that many people, but we had between 200 and 400 people there. And at that point, I know, okay, I think I'm beginning to believe this technology could be real. So it was an exciting breakthrough. So now we got to decide, though, what oxide electronic channel layer do we have to deal with? And we wandered through the desert on that for quite a while. Professor Hosano was saying IGZO is the way to go. We were looking at zinc indium oxide, had higher mobility, but very finicky material. I still like zinc tin oxide. That's a very, very nice material. I think it will have second generation applications. Applied Materials developed an interesting material, zinc oxynitride. All of our amorphous oxide semiconductors have disorder on the cation site. This one has disorder on the anion site, so that's interesting. And then zinc oxide and a whole bunch of others, but I'm going to eliminate that because I'm focused on amorphous, and I think amorphous is a key aspect of this whole thing. So Professor Hosano, he said, well, this is the winner, and he says the train is leaving the station. If you look carefully, he was actually the conductor on that train, and he says, please hop on. But he's changed his mind. Now he says, well, too late, we've left the station at this point. So yeah, if he's in the audience or some of the Japanese guys, they'll like that joke. You guys don't get it, but that's okay. So the two big giant applications are AMLCD display backplanes and AMLCD display backplanes. There's TFTs, there's millions of TFTs in the back, and all you need is you just need a switching TFT. And the switching TFT is pretty easy. You need a high on to off ratio, about 1 million between on and off. You need it to be manufacturable, and I'm arguing amorphous is the key to that. You need voltage control, or it's a voltage controlled switch, which is a very forgiving kind of application. Mobility is not that important, and stability is not that important. So it's a nice application. The other big, huge potential application are these AMOLEDs, active matrix organic light-emitting devices. And they're more complicated in terms of the pixel architecture. Here's an example of a pixel architecture which has 4 transistors and a capacitor. Okay, so it's a different kind of thing. 1 transistor versus multiple transistors. Manufacturability is still a key. I think amorphous is important, but this is a current control device. Remember, AMLCD is a voltage control device. Current control is just more difficult. Mobility and stability becoming more important. And really, what's going on with this circuit architecture is you're compensating for any OLED instability, materials instability, TFT instability, or TFT threshold voltage or mobility non-uniformity. So that's where that pixel architecture starts getting complicated because of those really materials problems. You're trying to solve materials problems with a circuit solution. Okay? So if I look at the backplane application, or backplane options, I've got amorphous hydrogenated silicon, low temperature polycrystalline, amorphous indium gallium zinc oxide. And those are the 3. Amorphous silicon has been the workhorse for the last 25 years. It's going away, it's running out of steam, and so one of these 2 are going to be the replacements. So if I look at it and compare, I look at the microstructure, and amorphous is the key to the success, I'm arguing, the key to the success of amorphous hydrogenated silicon. And the reason is you can get good threshold voltage uniformity, good mobility uniformity, and it's a simple process in terms of complexity. Same sort of thing with IGZO because it's amorphous. Now, right now, we don't have the uniformity of the threshold and the uniformity of the mobility because we're in an earlier stage. I'm confident that that will go blue is best, green is intermediate, and red is bad. I'm confident we'll go from green to blue as things emerge. Okay? Polycrystalline, I don't see it. I don't think it's going to happen. You know, you've got fair uniformity, and I don't think you can fix that. You've got high complexity. I know you can't fix that. So that's one of the differentiators between the 2. terms of threshold voltage stability, amorphous silicon, that's one of its weaknesses. It's not very good that way. We know LTPS is good, and we know IGZO is fair, but I would argue it's going to, as it matures, get good. So I think that's a similar kind of thing there. Mobility, LTPS wins. It's got the highest mobility. So if you need mobility, choose LTPS. That's the only way to go. However, we've got a lot more mobility than amorphous silicon in the IGZO, and I think there's a lot of application space. I'm very, very bullish about that. Device type, if you need CMOS, LTPS is the only way to go. So if your application requires CMOS, there's no other choice. But if you don't need that, it's gonna cost you to do that, okay? IGZO stability, I mentioned one of the issues in terms of stability, so let's drill down on that stability issue a little bit. Negative bias under illumination stress is the key question in terms of stability. So what does that mean? Well, if we have a log of the drain current versus the gate voltage, we call that a transfer curve. There's a nice transfer curve at about 0 volts there. What happens is if we do this measurement where we shine light, sub-band gap light, it's a below band gap, but it's near band gap, and if we apply a negative voltage, what we find is that that threshold voltage shifts way over, and then it persistently stays there, and that leads to all kinds of problems. If you look at an energy band diagram, the reason for that is you have some sub-band gap states, or sub-gap states, you get absorption in the sub-gap states, which creates electrons in the conduction band, holes in the valence band, and then I think mainly what's happening is some of the holes in certain insulators get in and trap charge, and it causes that persistent change in threshold voltage, okay? So how do you reduce NBIS? That's the problem for IGZO technology. First thing you do is you passivate the surface. Put something on top of your surface, don't leave it exposed to air. Next thing you do is you've got to reduce the sub-gap state density. Our group has found that a 400-degree air anneal is one of the most effective ways of doing that. You also have to choose a good gate insulator. Silicon dioxide, I think, is an excellent choice. Silicon nitride is a terrible choice, and I don't think hafnium oxide or aluminum oxide are also good choices. Also, you may have to do light shielding. In current amorphous silicon technology, they do light shielding. So that's something that you may have to wind up doing. Now there's another popular NBIS model out there, and it's kind of weird, but I'll go through it a little bit. It's called a negative U oxygen vacancy, and it's very exotic. If you like exotic things, you'll love this, because this is very exotic. So let's look at it a little bit. What the heck is this thing? So here's a normal situation. If I look at an oxygen vacancy, and if I think about the Gibbs free energy, or just the energy of formation of that, if I think about my Fermi level position, so here's the valence band, here's the conduction band, I'm moving my Fermi level up. It turns out that the energy it costs to create a vacancy depends on where you are, where your Fermi level is in the gap. Because what happens is that for a while the electronic state is double positively charged, then a transition becomes positively charged. Eventually it goes neutral. Once it's neutral, it doesn't care about the Fermi level. So this is the energetics of a normal situation. We call the separation in energy between those two, we call that the U, the energy of separation there. Now in rare cases, there's a so-called negative U situation. And the issue there is that those two have kind of flipped, okay? And so this state is now up here, it's no longer accessible. So what happens is I go from a double positive to a neutral state, and that requires 2 electrons. So again, this is a fairly unusual situation. It's known to happen, but it's unusual. And it's a metastable situation, so we got to go to some exotic explanations. This is trying to capture that. So this is the amount of optical energy we would have to supply to get it to go from its neutral state to double positively charged. But then what happens is there's a thermal barrier here, the thermal energy barrier. We say that's due to large lattice relaxation. So I have a vacancy cavity here. I shoot one of the electrons off, and what happens is the vacancy cavity kind of rearranges itself in a large lattice relaxation. that large lattice relaxation results in an energy barrier in which it's hard to get the electrons to go back in and to kind of kill that double positively charged. So that leads to an effect called persistent photoconductivity. Okay, I've done a lot of heavy lifting right here, and it turns out back in the 80s, EL2 and gallium arsenide, DX and aluminum gallium arsenide are two famous defects that this phenomenon is. And so what's happened is people have gone back and have just reinvented and reapplied that kind of, those kinds of theories. I think they've kind of misapplied it, and they say that, well, this negative U oxygen vacancy is the cause of this problem. I don't think so, because as far as I can understand, if you accept this model and use it, I would think you'd get as much positive bias illumination stress as negative bias illumination stress. And we see that you get a lot of this, but you get very little, if any, of that. So I just don't, even though there are probably 50 papers written on this, I don't buy it. I don't think it makes any sense. And even if you do buy it, the whole point is you really need to get rid of the subgap states. Whether that model is right or wrong, subgap states are the problem. You got to fix those in order to solve this problem with IGZO. Okay? So now we're going to go to the hype of IGZO. If you get a chance, and I don't know if we'll have time to do it here, go to that website and check it out. And then you can meet the IGZO man. This is really marketing hype, just way over the top. And I know our technology has arrived. You know your technology has arrived when the action figure shows up. So the action figure showed up. Go to the web. This is so much fun. You know, my family, they don't have a clue what I'm doing, but they get a kick out of the IGZO man. So go for it. But then after you see all the hype, you say, okay, they made a case for it. They actually took out an advertisement in the Wall Street Journal, and they make a very strong case for IGZO. So even after you see the hype. And here's another transfer curve where they show amorphous silicon, IGZO, and LTPS comparison. They say that here's the advantage of IGZO. It's got better mobility than amorphous silicon. The other advantage is you can turn it off more. It's got much, much less leakage, a couple orders of magnitude less leakage. And they say that buys you a whole bunch of stuff. Go and read about this. Higher resolution because you can make smaller devices. Less power consumption because you can stay up more off current. Another thing that they contend is really important, I think they're onto something here. Look, a lot of applications these days require touch. It looks to me like this off current, this low off current, is really going to revolutionize how people do touch. Okay? So looking at that a little bit more, we've got the increasing mobility here. So LTPS is the best. Decreasing leakage, IGZO is the best there. Let's look at that leakage a little bit more. Let's break it down to channel leakage and gate leakage and then compare those. The gate leakage, they use nitride in amorphous silicon. That's not a very good insulator compared to oxide. So oxide is better at LTPS, but LTPS has got roughness, so you're probably going to get more leakage there. But that probably doesn't matter. What really kills them is this. This is the issue. If you look at the band gaps are much different. And then if you go back and just look at what you expect the reverse current's going to be, or the leakage current's going to be, you have a bulk generation and a surface generation component, and you have that the intrinsic carrier concentration goes into that. The intrinsic carrier concentration depends exponentially on the band gap. So there's about an order of 10 to the 18 difference that you'd expect based on just this here. So there's going to be a lot less reverse leakage due to that, but it's even worse than that because silicon and amorphous silicon are bipolar materials. They're going to invert. So their leakage, I'm showing what their leakage really looks like. I was giving them a kind of a best case scenario. It's really going to look like this. So in terms of leakage, IGZO is the clear winner, and LTPS can't touch it. That's it. So one of the Sharp's issues is leakage is really important. If they're right on that, then IGZO is the clear winner, I think. I think it's more complicated. Mobility, though, mobility definitely LTPS wins. Okay, so we're almost done. So LTPS or IGZO, people have been asking that question here. And in terms of LTPS, if you need high mobility and you need CMOS, it's the only way to go. Choose that one. If you want to keep costs down, and if you want to scale to very, very large sizes, I think you're going to choose that one. The downside of IGZO is you have this negative bias instability, and it's not a proven technology. It hasn't been out in the field for a long time, so something could sneak up and bite you. The two downsides of LTPS are excimer laser annealing and ion implantation. If you can imagine, on these lines, they put a huge, huge ion implanter and excimer lasers. That's why it's one of the reasons their costs are so high. There's a lot of other reasons too. And one of the big things here is that it's really easy to insert oxide technology into an existing amorphous silicon plant. If you want to put LTPS in, spend $5 billion, build a new plant. Instead of taking the $2 billion or $3 billion plant, retrofitting it with a couple $100 million, you got to build a new plant. Economics are driving it. So LTPS or IGZO, I don't even think that's the question. Now I think it's IGZO for AMLCD or AMOLED. That's the question I want to ask. And so it turns out Sony is contending that you need a mobility of about 16 for, this is 8,000 ultra high definition at 240 hertz. This is a way out there kind of application. IGZO will handle that one easily. This is a paper by Sony. Another thing, another key question is the pixel architecture. Here's something, again, Sony is suggesting that a two transistor, one capacitor architecture may be sufficient for this in terms of independent control of the drive and write select lines. This is, I think, a new thing here. So I've got to conclude, LTPS or IGZO, well, I wouldn't be giving the talk on oxides if I wasn't going to choose that one, so that's not fair. But AMLCD or AMOLED, that's a harder one for me, and I'd probably go with that one because that AMLCD eats everything, you know, it defeats every other technology, and it's been doing it for 20 or 30 years. Now, I haven't completely given up on AMOLED. I'm rooting for it, but I think you need to have a simple pixel architecture, like a two transistor, one capacitor architecture if you're really going to have a chance on that. Okay, thanks a lot.